Activity 14.1 is penguin probability. This is a great activity to do with students as an introduction to probability. What you'll need is some dice and this game board, and you want to ask your students to divide up the penguins in a group. So if there's just a pair of students, they would each get 6 penguins. If there are 3 students, they each get 4 penguins, and so forth. Then you give them a pair of dice. Give them 2 different color dice. I think that's important for the explanation of the lesson, and you have them roll. So for example, I rolled a 6. So I'm going to mark an X above penguin number 6. That penguin wins this race. I roll a 7. And they can take turns rolling, but every student will mark the same winner for each round. So you don't skip anything. When you're done, kind of looks like a bar graph. Okay, I have 7 again. So you get the idea. You keep playing this because you probably don't have dice lying around. I've created this online game for you, and we're going to go to that one next. Okay, so this is the game, Penguin Race. You have your 12 penguins. We will roll the dice. Roll the dice. Here's a sum of 10, and you'll see that puts a little fish next to penguin 10. Roll the dice again, sum of 7, so forth. So, and you keep rolling. You'll see all the different penguins win. One of your students going to go, hey, I had penguin number 1. Why can't it win? Good opportunity to discuss why you can't get a sum of 1 when you roll a pair of dice. So I don't have. Oh, penguin number 6 wins. So I'm just going to transfer this right now onto my page. Do not copy mine. I want you to do your own. And you're going to go ahead and copy your results. Okay, so this is what mine looks like. Yours should look different. Probability that you actually have the exact same rules for each penguin is really, really slim. What I did, it took 49 rolls. I counted how many times I rolled the different sums, and we're going to add that to a spreadsheet. So I'm going to go to the spreadsheet and show you where to enter your data. Okay, so this is the spreadsheet, and you will put your name, just put your first name and your last initial. So everybody will go to the top row and enter your name, and then you will enter how many ones you had. So this is my data. And you'll see some other people have already played this game that have entered their data. Two and 2. I must have miscounted. So enter your data and then go back to your handout. Okay, so answer the question below, which penguin won? Well, for me, that's penguin 6. Was this a penguin you thought would win? Well, I had 6, 7, or 8, so yes. I mean, 6 and 7 were pretty neck and neck for me. Okay, so there's a lot of tables on this page, and because we're not in a classroom, table 1 is individually within, that is what you just did. So you should enter your data. I wrote it on the first sheet, but just do the same data. You just your data. This is your data. What I'm collecting is not class data. It's like everyone's data. So this is data from the spreadsheet. So the spreadsheet that's linked, it should be a 0, but go ahead and enter whatever time you do this, enter what's available to you at the top of that spreadsheet. Notice any patterns in the table, figure that out, and write those below. So that's up to you. What we're going to look at next is what we call a sample space. These are all the possible outcomes for this experiment. The experiment is rolling a pair of dice. So we're going to do this in a list, and you start with a curly bracket. The reason I said to roll 2 different colored die is because this one's green. A 2 on green would be different than a 2 on red. A 5 on red is different than a 5 on green. So we're going to do ordered pairs of points. And I'm going to start with the first row. 1, 2, 3, 4, 5, 6. And for each ordered pair, I'm going to use my red and green. So let's say I use red first and I roll a 1 on red. Then what's possible on green is I could roll a 1 or a 2 or a 3, 4, 5, or 6. And that is having a 1 on red. So let me do this again. But now we're going to roll a 2 on red. And then that 2 can be combined with a green 1, 2, 3, 4, 5, 6. So what we're looking at in different colors is, as I mentioned, a red 1 and a green 2 is different than a red 2 and a green 1. If they're the same number, like a 1, 1, 2, 2, you only need one of them. You will continue this pattern. For all 6 numbers you can have on red, and you will combine that. Okay, so that's row 3, 4, here's 5. And here is 6, and then we'll close it. And put a bunch of commas in between. So I take a minute to do that. You do the same. So now that I have my whole list completed, I'm going to fill out the number of ways you can roll. A sum of 1 would be 0. You can never get a 1 when you roll 2 dice. A sum of 2 is only 1, 1. There's only one way. A sum of 3 is you'd either roll 1, 2, or 2, 1. So 2. A 4 is up here. Notice how you have these nice patterns on the diagonal. A 1, a 3, 2, and 2, 3, and 1. That's 3. 5 is right here. 1, 2, 3, 4. 6 is 1, 2, 3, 4, 5. 7 starts in the top right, goes all the way to the bottom left, so that's 6. And then 8, you start below, go all the way, so then it's 5, 4, 3, 2, 1, because there's only one way to roll a sum of 12, and that's 6 and 6. The probability, and this is talking about the theoretical probability, not what we got doing our experiment. The theoretical probability is the number of ways a certain sum can happen over the total number of outcomes in your sample space. So if you look at your whole sample space, you have 6 outcomes in row 1, 6 in row 2, and all the way down. So we have 36 outcomes. That means rolling a sum of 1 would be 0 over 36. 1 over 36. 2 over 36. And all the way down to the end. When you are done and you add all these fractions, I'm not simplifying them because when we add them, we should get 36 over 36. Now, for us, it's easier to think about probability in terms of percent versus fraction. We'll do most of them in fraction form, but for this activity, we want the percent. So on a calculator, you do 1 divided by 36 times 100, and that would give you the percent. So I'm going to go ahead, use my calculator. So this is just 0, but 1 divided by 36 times 100 would be 2.7 repeating, and that's a percent. That also means that 12 is 2.7 repeating percent. When we add them all up, oops, sorry, they should add up to 100%. So do this for each of them. I'll give you a minute to do that. I'm going to do the same, so pause and complete the table. Once you have all your percents, you want to fill out the bottom table from the spreadsheet. So go back to that link and you figure out at that given time the total, the fraction probability, and the percent probability. And then once you have filled that out, you want to compare our experiment, that's the spreadsheet, to the theoretical probability, which is what I just completed in that top table based on the theoretical probability of rolling all these different sums. So answer the following problems based on the sample space and the table for the theoretical probability. When rolling 2 fair dice and taking the sum, how many possible outcomes are there? There are 36 outcomes. What sum has the highest probability of occurring? That is a sum of 7. And when I said we're better at percents than we are at fractions, because a sum of 7, here's a 7, has a 16.6 repeating percent probability of happening. 6 out of 36 is the highest probability in this table. What is the probability that the sum is 9? So I'm going to go back to my table because it's based on theoretical probability, and a sum of 9 is 4 out of 36. Now, we know MyLab Math's going to require us to simplify our fractions. So divide top and bottom by 4, you get 1 over 9. When you answer these, answer them as fractions, not as percents. Percents is really what we do when we're trying to compare numbers because we're just better at comparing percents than fractions. What is the probability that the sum is an odd number? Well, we can't get a sum of 7, so the smallest odd number we can have is a 3 or a 5. Or a 7, or a 9, or an 11. So I'm going to look in my table and figure out the theoretical probability of rolling these different sums. So again, I'm using the table on the previous page to find these fractions. A 3 is 2 out of 36. A 5 is 5. A sum, nope. That's a 4, looking at the wrong one. A sum of 7 is 6, sum of 9 is 4, and a sum of 11 is 2. If it's an OR statement, you will add those probabilities together. So 2 plus 4 is 6, that's 12, 16, that's 18. We simplify with this one half. Half of your sums are even, half of your sums are odd. What is the probability that the sum is greater than 7? So greater than, strictly greater than. So that means you have 8 or 9 or 10 or 11 or 12. You go ahead, they're all going to be over 36. Go ahead on the previous page, find a probability for each of these sums. Get an answer. If you can simplify it, simplify it. And that's the end of the penguin probability.